We are very pleased to have him here to speak on the landscape response to bioclimatic changes over the past 13,000 years in the central Great Plains of North America.
Thank you, Alice and Dan, for inviting me. It's an honor to be here. It's been a real learning experience for me. I feel like a student this afternoon listening to all these wonderful papers. I've not worked in the northeastern part of the U.S., and so I've learned a lot. I've heard a lot about ice, but I'm going to tell you, you're not going to hear much about ice from me. We're talking about a non-glacial landscape, Kansas, Nebraska. I will say that the eastern extreme portion of Nebraska did experience glaciation, as did the northeastern corner of Kansas. And in fact, my only claim to claim might be that my house sits on the southern limit of glaciation in North America. It literally sits on the end moraine for pre-Illinois glaciation, which it predates 650,000 years ago, so a little bit older than me. Anyway, so I'm really talking about the Central Plains. This basically what I call the Central Plains is Nebraska and Kansas, and I've spent a lot of my career there. This is a map of Kansas, Nebraska. You see all these numbered spots. There's about 50 of them on there. These are all stratigraphic sections where I really focus primarily on the Pleistocene transition and buried Paleogene landscape. Unfortunately, I'm just not going to have a lot of time to talk about geoarchaeology, which is, of course, one of my favorite topics. I actually am going to show you some sites. But I'm really going to focus more on fluvial geomorphology, soil stratigraphy, climatic reconstruction. I may hold the record for the greatest number of slides at a Barnes conference, okay? So hold on to your seats, because I'm going to go pretty fast here. I've got a lot to show you. I've got a lot to share with you. I hope you find it interesting. So there are really two questions I want to address here. What was the nature of bioclimatic change in the Central Great Plains during the Younger Dryas? It's an area I'm particularly interested in, and actually the entire Holocene. And how did stream systems and alluvial landscapes respond to those changes? And so the area, again, that I'm focusing on here is right in here. And as you can see, there's a very steep longitudinal precipitation gradient going from a moist subhumid climate in the extreme part of eastern Kansas and Nebraska, where you get about 34 to 36 inches of precipitation per year, to when you get out into the western high plains, you're looking more at about 12 inches or to 10 inches of rainfall per year. So you're getting into a semi-arid environment. And so it's not surprising that the vegetation, ecotones, respond to that precipitation gradient. What you see going from the eastern part of Kansas, Nebraska, you see tallgrass prairie, and actually there are islands of oak hickory. So it's really more of a mosaic in this portion. But as you work your way westward, you go into more of a mixed grass prairie and then finally into a short grass prairie. But this is an ideal place to look for bioclimatic change because these boundaries, these ecotones, fluctuated back and forth. When it got drier, the short grass prairies moved eastward. When it got wetter, the tall grass prairies moved westward, as did some of the trees. Okay, so it's a great place to do a bioclimatic reconstruction. The other thing I want to talk about a little bit too is we're in a pretty unique setting in terms of weather phenomena. Of course, everybody always thinks of Kansas tornadoes, right? Big mid-latitude cyclones, these big storm systems that come through. The reason for that is that we're really at a conflict zone between, we get these polar outbreaks, we also get Pacific fronts that then collide with warm, moist Gulf air coming up, flowing longitudinally into the mid-continent. And this generates really, really big storms. And this is actually an important part of my story here. This area is really famous for intense rainfalls. This is Kansas City, the Brush Creek flood in September of 1977. Now, granted, some of this was promoted by urbanization, but this was a 14-inch rainfall in about 6 hours. That is a lot of water falling in the sky. And these sort of events are really not that rare because of what I just told you about this conflict zone. In this case, it was a polar outbreak that collided with a big incursion of Gulf air and generated a tremendous amount of rainfall. But this is something that's really important to the story I'm telling you. Because what happens, again, my area of expertise is fluvial geomorphology. When I go out onto the modern floodplain, this is the Big Blue River in eastern Kansas, and it may be difficult to see the scale here, but we're down to about 4 meters below surface. And what you see are all these flood drapes. These are upward finding sequences, sands to clays. These lighter zones are sands to clays. And what's interesting is at the bottom, we actually found fragments of barbed wire that were dated to about 1920. So all of this accumulated, this 4 meters accumulated since 1920. It takes a lot of water to do this, to generate that much sediment, deposit it. And what you don't see is any indication of stability. I mean, this is piled up. So you don't see any buried soils in this, no A horizons. All those dark zones are just flood drapes, okay? And so what I want to do is compare that to more low magnitude flooding. This is seasonal flooding on the Missouri River. We get these sheet floods. They're relatively low magnitude. And the reason why this is important is I want to talk about cumulic soils versus non-cumulic soils. And I don't know how many of you have studied pedology in this room, but I'm going to give you a real quick lesson on this, okay? Hopefully this animation will work. So we're going to start with what a cumulic soil is on the left. So here we go. What a cumulic soil is where when you get low magnitude flooding, you get a small amount of organic matter added to the surface and periodically interrupted by maybe some stability and plants come in. And this is what we call soil upbuilding. So what it does is this generates, and I'm going to show you what it looks like, a very organic, rich cumulic soil that may have even some sedimentological properties. You might even see really fake bedding within a cumulic soil until it finally stabilizes. So it's really, like I said, an upbuilding process. The common denominator is you get a really overthickened A horizon versus a non-cumulic soil, which is like this. The sediment all piles up, plants come in, organic matter through roots goes down, through bioturbation goes down, animals adding a little bit of organic matter to the surface. All that organic matter finds its way down. So my point is this soil looks much different than this soil. And you cannot have high magnitude floods to produce this. I'm going to show you just a real classic cumulic soil. This is along a stream in east central Kansas along Allen Creek. And we're going to look at this section right here. And that is a 2 meter thick A horizon. And there are actually archaeological deposits stratified through it. And so this is a product of very slow aggradation. And people occasionally came out and lived on that surface, and they got buried, and producing what is commonly referred to as overthickened A horizon. My point is that you cannot get this sort of soil forming with a lot of big high magnitude floods. Otherwise, you'd see a lot of bedding, sands, upward finding sequences within that. You don't. Whereas up here, all of a sudden you get a big pulse of sediment, it's stratified, then a kind of a thin cumulic soil, and a final pulse of sediment. So kind of keep this in mind with what I'm going to show you here in a bit. Proxies for bioclimatic change in central plains. When I flew into Bangor, I noticed looking out the window, I saw lots of bogs. I'm assuming lots of peat bogs, marshes, and we suffer from I have bog envy because we have, in Kansas, we have one peat bog in the entire state. It's been reported. Northeastern Kansas, Muskota bog, which Jan Brugger and Herb Wright studied back in the early 70s. It has a pollen record that goes back to the LGM. The Holocene part's a little bit sketchy. Spring activity tended to mix it a bit. So anyway, pollen is just not common in Kansas in terms of pollen records. So you have that luxury here. But I got better sections. I got better alluvial sections than you guys. I'm going to show you in a second. So we turn to other proxies. I do a lot of chemostratigraphy, isotope geochemistry, specifically with soils, looking at the isotope signal soil organic matter, because we know that C3 plants, trees, also cool season grasses, that organic matter ends up in the soil. and just as it does with C4 plants. And then we have different ranges, the delta 13 values, minus 26 to minus 22 for C3s and minus 16 to 12 for C4, and then we have mixed C3, C4 in the middle. The reason this is important is that, as you're going to see, I'm going to show you lots of buried soils. And by looking at the values, the differences in these soils, we can determine whether the plant community was more C3 dominated or C4 dominated. Okay, so that's an important part of the story as well. We also have phytoliths, usually well preserved in these soils, which is biogenic opal. And we can, at least with the major grasses, we can look at chloridoids, which are these warm season C4s, panicoids, also C4s, but poeds, the C3 grasses. And Carlos Cordova at Oklahoma State, we've been working together. And he's actually been looking also at trees, at phytoliths produced by trees, and he can separate by genus. He can separate pine from spruce, looking at the phytoliths, and also from deciduous trees. So that's part of the story here as well. And then also gastropods, the land snails, are pretty powerful tools. They're sensitive to both temperature, especially number of frost-free days, and they're also moisture sensitive. So they're also very good proxies. And oftentimes we do see good preservation of gastropods. The other sort of preface here is, before I jump into things, is that we have a lot of loess, windblown silts. There's the Kansas landscape. It's not quite that bad in eastern Kansas. It's not quite that flat. Actually, it looks a little bit like the landscape around here in the eastern part of the state. But there is a lot of loess. In fact, in southwestern Nebraska, that's the thickest loess in North America. It's greater than 20 meters thick. And it's fact, China is the only place that has thicker loess, the Yellow River Valley. And so there is a lot of loess that blankets this landscape. And to kind of put this into perspective, that's me right there. This is loess from there to the bottom. That's all dust. That's all windblown silt. You thought your place was dusty. You can only imagine what it was like during the Pleistocene. So anyway, this is important because loess is highly erodible. And so when there was climate change, especially when it got drier, a lot of erosion, a lot of this ended up down in the river valleys. And we see that signal in the alluvial record. Okay? Okay, now to cut to the chase. So what was the nature of bioclimatic change in the Central Great Plains during the Younger Dryas and Holocene? I'm going to answer that first, and I can't show you all my sites. So I'm going to show two at opposite ends of the state. Colossal in the east, Canerado. Both of these are archaeological sites, pretty significant ones. And we're going to begin with Canerado. And this is right, basically the Kansas-Colorado border is right there. And this is I-70, and so crosses the site, actually 3 sites. When they straighten the channel of Middle Beaver Creek, I'm standing up on the uplands looking down. This is all shortgrass prairie, and this is a straightened reach, and there's a buried soil that dives to where you can see all these people standing. And there I am looking down at bones in the bottom of the section. That, by the way, is Joe Kramer, who created the endowment that I'm in charge of. And this is what I'm looking at. There are mammoth bones. You can see one sticking out of the wall here. These are camel. This is American camel. And I'm looking for artifacts because all the dates I'm going to give you are in uncalibrated radiocarbon years PP. So, Clovis is the oldest, is about 11,500. So this was intriguing. And while there were no lithics, there's a lot of evidence, at least, of bone modification, green bone spiral fractures, some bone tools. With the lack of lithics, some archaeologists will never buy it as pre-Clovis. But I'm going to leave it at that. But it's a really interesting stratigraphic section. So this is where the mammoth and camel bones came out. This is actually the first stratified Clovis and Folsom site. But I want you to notice this really thick humic soil that began to degrade around, close to 11,000, stopped around 9,200. There's sedimentation. There's another weak soil here with a middle archaic component, and then it got buried. This is a really consistent pattern. You'll see this as I continue. So we looked at phytoliths and also stable carbon isotopes here. I hope you can see this. This red curve right here is the isotope curve. And you can see it starts out in the lower part. This is around 12, a little more than 12,000, 12,300. It's a pretty strong C3 signal that shifts. As we get to the younger Dryas, it actually is getting progressively warmer based on the isotope record. It kind of stabilizes and then kind of swings a little bit back to C, more of a mixed grass, a little more C3, and then just really gets warm. Really strong C4 signal minus, approaching minus 12 at the top. And so looking at the phytoliths, what's interesting is that they really support the isotope record in the sense that we start out here when it's cooler and presumably wetter, that there's a lot more woodland. And based on the phytoliths, spruce and pine predominantly, until we get up to close to 11,000, and the spruce and pine give way to deciduous species, trees. And then it really starts to dry out. And the chloridoids are really important because these are the short grasses. And you can see they really start ramping up just before the younger Dryas, and then kind of stabilize and then really ramp up during the early to middle Holocene. Whereas the pods, which are your cool season grasses, do just the opposite. They're pretty strong here and they drop off. So we see the shift actually that began during the early part of the younger Dryas, where it's getting warmer and presumably drier, and continues pretty much through the whole period of record that we have there. What's also interesting is are the land snails tell us a story. Jim Thaler at University of Wisconsin La Crosse is still analyzing it, but he's gotten far enough to tell me at least this part of the story, that so these, again, uncalibrated ages, from 12.4 to 11, an abundance of aquatic gastropods, the presence, I'm not even trying to pronounce it, indicates ponded water, perhaps seasonal. But by 10.9 to 10.3, aquatic species gradually decline in number at the expense of terrestrial. It's getting drier at Colorado. And then by 10.3, aquatic species disappear from the assemblage and are replaced by terrestrial land snails that prefer dry environments. So it pretty much supports both the phytolith and isotope record. And that's what you like when your proxies support each other. So this is what it probably looked like. If you went back 12.4 to 11,000, we had mammoth, we had the remains of mammoth, we had camel as well. Kind of a quiescent environment, spruce and pine with cool season grasses, fairly mesic. And then by 10.9 to 10.3, we see a shift. The pines and spruce disappear, the number of trees decline. We have deciduous trees, although it's still a relatively quiescent environment. There's pools of water that have been attracted to those animals. And then, there it is, by 10.3 to present, of course at 10.3 the interstate wasn't there, but it was, short grass prairie, certainly by 10.3 based on all the evidence we have. It got really hot and dry by 10.3, and it's been that way pretty much through most of the Holocene. So jumping eastward to the Colossal Site, so we're getting into more of a moist subhumid environment. Rainfall there is about 32 inches per year. Colossal Site, it's located along Mill Creek, right here on a big bend in Mill Creek. We'll kind of zoom in on it. We're looking at a big cutback. This is one of the big sections that typifies a lot of the streams in Kansas. So you can see that there's a person standing down here pointing to the top of the buried soil. There are multiple buried soils. There's one there, there's one there, there's one there. We know that the surface of this alluvial terrace stabilized soon after 4,000. And so looking at it from another direction, there's archaeology buried in that lower buried soil. And what we see at that point is this thick cumulate A horizon. And it's got archaeology here, it's got archaeology here. And then all of a sudden, it becomes stratified. And it's like that all the way up to the next buried soil. So sediment really started to pour in. The rate of sedimentation rapidly increased. This, again, is a product of very slow aggradation. This is the excavation into that buried soil. There are, as I said, at least two components. There's one up here. There's a denser component with a scatter of mussel shells, as you can see here. And looking at it in plain view, okay, so this is a mussel shell midden in Kansas, Jackie, and that was 1 shell thick. So we are sort of mussel shell or shell midden challenge in Kansas. I'm almost embarrassed to show this after the talk yesterday. But anyway, that is a mussel shell midden. And that's that boundary between this big, thick humic soil and basically rapid sedimentation soon after 8900. It also yielded a Dolphin Point and a Dolphin Abs as well right next to it. But what makes this significant, this is the westernmost occurrence of Dolphin, which is middle to late Paleo. Dolphin is really common in the Ozarks. So we know that Dolphin people spilled out of the Ozarks out into the eastern plain. So from that perspective, it's a really significant archaeological site. We look at the isotope record and the phytoliths, and we see here, this is the isotope curve. We can see the values here are about 20. As we go up into this buried soil with all the archaeology in it, it swings back a little bit more C3, and then just kind of steadily ramps up to more, by the top here, a strongly C4 signal. So it's getting warmer. The phytoliths also tell us that it's getting drier. You're getting into there's very few chlorinoids here, but quite a few up here. Strong POIDs signal here, much less so here. So again, in this case, the phytolith and the isotope data complement each other. This is Paul Goldberg. He came out to the site. Some of you, I think, know Paul. Collecting a block of soil to do thin section analysis next to my beautiful mussel shell midden. And there's Paul looking really happy. He always has that smile when he gets a good sample out. The reason actually I want to show you this is when you look, hopefully you can see this. It may be difficult in the back room, but there are little white dots all through this. There's one up there. There are literally thousands of gastropods, land snails in this. So we got excited about that. So, and Jim Thaler kind of moaned when I sent him the samples with thousands of gastropods. I told him to analyze these, please. And so anyway, so he's completed the analysis. What we see is that these land snails, the ones you see here, dominate the colossal assemblage at 10.5. That's the oldest date. There was a feature at water level that dated to 10.5. It's probably a Folsom hearth that has these species, which are typical of moist woodland settings. This species demands a moist environment and is common near springs or seeps. So then we see a shift from 10.5 to 9250. This species becomes less common and eventually drops out of the sequence with this species, the woodland land snail, that prefers drier environments compared to that one. And so this one becomes the dominant species. So it's getting drier. And then between 9250 and 8900, we see that this species and this one, this one is a species that requires a growing season of 160 frost-free days. The land snail assemblage is indicative of an open, dry setting with prairie to brushy vegetation. And of course, this date is significant because this is when we see that change in the alluviation from we're getting out of that humic soil into rapid sedimentation soon after 8900, okay? So the findings at Quaternary suggest that there was a warming and drying trend in the west central plains that intensified through the Younger Dryas, so from about 11 to 10,000 radiocarbon years BP, and continued into the early and middle Holocene. Whereas the findings of the Colossal Site suggested a warming and drying trend was underway in the east central plains by 8800 and continued into the early and middle Holocene. So there's time transgression going from west to east. It seems that drying trend began about 1,000 years later in the east compared to the west, which is a point I'm going to come back to at the end of the talk. So how did stream systems and alluvial landscapes respond to those changes? The approach that I take when I'm doing an analysis of the temporal and spatial patterns of landscape evolution in streams is I take a basin-wide approach. So I'll take an entire stream basin like this one. This is the Pawnee River drainage basin in southwestern Kansas. And I look at low order streams high in the drainage network, and I work my way down through the whole system, looking at stratigraphic sections and cores. And so wherever you see a yellow square is a place where I did some analytical work looking at sections or cores. And so I'm going to begin with low order streams, excluding draws on the Luss Mandel high plains. These are less than fifth order streams. And I'm not going to spend a lot of time talking about these small streams because they're extremely repetitious. But this is Buckner Creek in southwestern Kansas. There's a modern floodplain. This is the first terrace. And the area in the background are the uplands, the Luss Mandel uplands. So this terrace spans the entire valley floor. If you look closely, you can already see a buried soil right there. We're going to zoom in on this. And there, by the way, there's a heart sticking out of this one. There's archaeology here. There's archaeology here. There's a really pissed off badger here. And that became a nuisance or a threat. Here are the radiocarbon ages. You know, this is a pretty big section. That's a 2 meter long shovel. And bedrock is just below the bottom of the exposure here. My point is that all of this alluvium is late Holocene. It's less than about 3,000 years old, the bedrock, okay? Now I could go on and show you like 50 other localities that look just like this all over Kansas, Nebraska. So I'm going to cut to the chase, instead show you a histogram. This was my results in 98. The end value was more than triple, but the histogram, I was just lazy and didn't produce another histogram because it doesn't look any different. I can tell you that I still don't have any dates from small valleys. These are all my radiocarbon ages from charcoal, dating soils, dating organic mats at the bottom of alluvial fills. I have none that are older than 7,000. The point here is that this period from 11 to 7, the alluvium has been removed by erosion. And I think this is really a geomorphic signal of the altithermal. And I'm going to come back to that. But this was a period of intensive erosion that basically removed the entire record, predating 7,000. For that matter, we don't really have much from 5 to 7. But then we see a change in the late Holocene that these small streams, less than fifth order, became zones of net sediment storage. So net sediment removal to net sediment storage. Again, I'm going to come back to this and hopefully explain it in a little bit more detail. High order streams, greater than fifth order, so we're getting to big valleys. I'm going to show you this monster stratigraphic section down in along the Chicaskia River. There it is. This is 13 meters. And there's this cumulative soil. There it is. I'm in close-up. Dates, this is on soil carbon, 10.8 to about 10,000 near the top. And you can see dates, these are all in buried soils, about 8,000, 7,000, a little over 5,000, and 1,000. So pretty much the entire Holocene record is in this one section, which was an incredible task for me to clean off. But I did it and survived. But I'm especially interested in this cumulative soil at the bottom of the section. This is where Paleo-Indians would have been walking. Of course, this is all the sediment that poured in during the Holocene. You can see a lot of bedding in it too. There's a lot of bedding between the buried soils. So sedimentation just ramped up after 10,000. Something happened that triggered extremely rapid sedimentation to produce this much alluvium. Okay? I'll take you a little bit to the north, the Saline River. We're going to take a look at this section up close. Really what I call there's actually multiple A horizons in here. A pedocomplex, 10.6 to close to 10 near the top. And then sedimentation ramps up and stops briefly, 82. And then there's an unconformity right here, where late Holocene alluvium is sitting on early Holocene alluvium. This is not unusual. I often see this unconformity in these large rivers. The Saline River further west, another big section. Some date on charcoal, 12.9, but look at this. Again, here's the younger Dryas. 11,000 to not quite the end of the younger Dryas, and then a big pulse of sediment, 6,000, 5,000, 3,000. So a little more of the Holocene record here. But again, this cumulative soil. So just to sum up all these, looking at all the radiocarbon ages, this was in 2002, and I had more dates. I have more than 439 now, but again, the histogram hasn't changed. So we see actually quite a bit of early Holocene alluvium, not a whole lot in the middle. So that's that hiatus, that unconformity, and then quite a bit in the late Holocene. Alluvial fans, one of my favorite topics. I've spent a lot of time looking at alluvial fans. Every one of those dots is a stratigraphic section I've looked at in an alluvial fan. And so here we are in western Kansas. I'm testing, you see who's still awake. No, that's Death Valley. But I love alluvial fans because they are actually the link between what's going on in the uplands and what's going on down the valley floor in terms of sediment yields. So, you know, I'm going to show you what a real alluvial fan looks like in Kansas. Here, Adams Ranch fan. If you look closely, there's an alluvial fan right there. The Cimarron River has migrated laterally to move the distal, totally removed the distal end, but for me, created this beautiful window into the midsection of the fan, which I'm going to zoom in on. You can see it there. This is, to be honest, this is as good as it gets with an alluvial fan in the Central Plains. This is as big as I've ever seen one. And so, oops, let's see. I thought I had the dates, but I'll back up. Somehow they vanished. Anyway, where we are in time here, this buried soil dates to about 12,000, and then we get to about 10,000 to about 9,000. The bulk of everything above it accumulated after 9,000 years BP. The slide I'm looking for may show up in a minute. Willem's Ranch fan. This is up in the northwest corner of the state. Also, not overly impressive. Here's one lobe. The other lobe was removed by the creek as it migrated laterally. But a nice. Oh, here's the image I was looking for. This is actually the one from the Cimarron, which shows these dates: 12.6, 12.5, 10, 9, and then rapid sedimentation after 9. But this is the Willem's Ranch fan. Note the cumulative soil. Here's the younger Dryas right here. So 10.7, 10.4, 92, and then rapid, a little bit more rapid sedimentation, 65, and then really rapid sedimentation after that. Eagles Roost fan, the last fan I'm going to show you real quick. This is one of my more eastern fans, and 7,100. So this is kind of filling that gap that you see in the small streams, also in some of the large ones. But I also want to point out near the top, around 4,000. Just about every fan that I studied, by between 4,000 and 3,000, they stabilized, and no more sediment was being delivered to them. That's a common denominator with all the fans I've looked at. So by the time you get the late Holocene, there really is no more delivery of sediment to them. They're stable surfaces. That's also an important part of the story. Finally, draws on the high plains. These are these dry valleys that are way up at the tips of these low order streams. And although a tremendous amount of sediment is stored in them, all of this is Holocene and late Pleistocene, very terminal Pleistocene alluvium. And it goes for many, many miles, the uplands in the background. Here's the section. I'm going to plug in the radiocarbon dates, look familiar. Notice the big, thick cumulative soil at the bottom. You know, that's the bulk of the younger Dryas. And so soon after 10,000, sedimentation really ramps up, pauses, ramps up, stops, and so sometime after 8240, it's stabilized. This is Sand Creek, another draw. Look from there, big, thick cumulative soil, actually multiple soils that are all welded together, 11.7, 10.6, so, you know, the younger Dryas. And this all looks like it's late Holocene. You know, there's very little soil development, it's all stratified, came in fast. And then finally, Beaver Creek, another draw. We're going to look at this section here and look familiar. Big, thick cumulative soils welded together, 10.8, almost 10.9, 98, 91, and then rapid sedimentation. So by now, you should see there's a pattern, right? And we look at the results in 1998. This is what I showed you earlier. And then we add the draws. There's the draws. We still have this big gap. So basically, the waves of incision during the early to middle Holocene never reached up into the very fingertips of the drainage network. That's why this record is preserved there. So what's driving it? You know, we're not in a tectonically active area, so we can't, you know, in terms of the fluvial system, it's not tectonically active. We're too far from the ocean, so sea level is not a factor. So climate, there are also internal geomorphic thresholds involved, but you know, climate is the big driver here. And so, these are the conclusions. I say here the ubiquitous cubic soils dating between circa 13,000 and 9,000, again, radiocarbon years BP, indicate that moderate to high magnitude flooding did not occur in the central plains during that period. Atmospheric mechanisms that form the latitude cyclones were not in place until after about 9,000, certainly in the eastern part, and maybe 10,000 in the western part. So this is a map from COMAP that shows the glacial anticyclone in July, and that this cold air that's spilling out of here is pushing the jet stream. It's actually controlling the mean position of the jet stream, which, by the way, it kind of runs right through Kansas. It moves slightly, but its mean position, which is why we have a lot of tornadoes, right, in Kansas, because the jet stream, which is the storm front, is positioned over that part of the country during that time. So we get a lot of cyclogenesis during the spring and summer. So what I'm going to show you here, what I've done is I've sort of reconstructed where I think the jet stream was, pushing back in time. And I've based this on interacting with a lot of my colleagues who've looked at the alluvial record further south of Kansas. And I've concluded that in 11.7 at least, or 13.5 in calibrated years, that it was down in, you know, this is in the northern part of Texas. And through time, as the ice sheet retreated, what happened was the storm front, the jet stream, migrated northward. And so by 10.3, we see that it's pretty much in the area of Kansas. And so I think that basically, this is my only ice story here today, is that the position of the ice sheet, you know, strongly controlled the position of the storm front, the jet stream, which brought these mid-latitude cyclones into the mid-continent as we're coming out of the Pleistocene into the Holocene. And that Jim Knox, who I guess you could say I'm a academic grandchild of his, because my advisor, Kurt Sorensen, was one of his students. So Jim had a strong influence on Kurt and me. And he has this paper where he talks about responses of fluvial systems to Holocene climates. And he was really focusing mainly on the upper Midwest. But the story that he produced really explains a lot of what I just showed you, in the sense that, and these maps, these two maps, are based on work that Reed Bryson and Hare prepared. And what this shows is that as you get into the early through mid-Holocene, you see this dominant zonal airflow from west to east. And as that air flows over the Rockies and descends, of course, it heats adiabatically, so we get this warm, dry air that pushes eastward. And you know, when we have droughts in Kansas, this is the dominant airflow. And what Knox said was, well, pretty much during early through mid-Holocene, this was the dominant flow. And that pushed the shortgrass prairie eastward and pushed aridity, in other words, pushed the altithermal eastward. What I would say is that that's true, although it was time transgressive, it just didn't happen all at once. Remember that 1,000-year lag I mentioned between western central plains and eastern? It took about 1,000 years, I think, for it to cross Kansas and Nebraska, the mean position of that zonal dry air. What that did, though, was it reduced vegetative cover on the landscape. It got really dry and hot. Short grass prairie, frequent fires. We see that actually in the charcoal record. A lot of devegetation of the uplands. So what did I tell you the uplands consisted of? Bluffs, right? Highly erodible. And when you get into a system of airflow like this, when you do get mid-latitude cyclones, they tend to be really intense, short, intense storms. Think about these small streams, these low-order streams, steep gradients. The sediments is literally getting flushed out of them. Where does it go? Well, I showed you where it went. It's being stored in alluvial fans, and to some extent in the high-order streams. It has to go somewhere. That's why it's important to look at it basin-wide. Okay, so then we shift into the late Holocene. By around 4,000, we see that there's more of a longitudinal flow of air. In other words, Gulf air is penetrating. Incursions of Gulf air are working up into the mid-continent, cutting off the zonal airflow. And so precipitation increases, temperatures decrease, vegetation is restored on the uplands are stabilized, sedimentation from the uplands is reduced, and guess what? The alluvial fans stabilize at that time. The small streams become zones of net sediment storage. So we see this landscape response to these two different types of dominant airflow patterns, which may seem oversimplified, but I think Jim got it right. This had a really strong influence on the alluvial record that I just showed you. So, okay, that's a mouthful. I thought I'd end by, I don't think this is the state symbol of Kansas. The reason I wanted to show this is that for the archaeologists in this room, I will claim that Paleo-Indians never saw a tornado because the mechanism to produce it didn't exist during Paleo-Indian time. So it was the archaic people who probably witnessed tornadoes. So on that note, I'll end. Thanks for your attention late in the afternoon. Dan, you got your arm out first, Dan.
All right. So you've got this clear zonation through time of these bioclimatic changes. Is there an obvious human response? Intensity of occupation, lifeways?
I would say lifeways in the sense that, it used to be that, and really not that far in the past, before I'd say 1975, the conventional wisdom was that people abandoned the Central Plains during the Alt-Thermal, from 9,000 to 4,000. People got, the concept of the Great American Desert, and that people weren't there. The problem is that the record was either removed from small streams or was deeply buried in alluvial fans, because I found it in alluvial fans, in the draws, and also in some of the large valleys. I think people were tethered to places where there was water. In other words, near streams. We see a lot of occupation near springs. So, there were hunters and gatherers, but I think they probably stayed pretty close to water sources, because I think it may not have been like the 1930s, but I think for that long stretch, it was pretty darn hot and dry. And so they would have been confined. But on the other hand, the bison were probably pretty happy because they love shortgrass berry. And so the bison population, there's some evidence, actually increased during that period. So there was plenty of food, just that you'd have to be near a water source, which makes sense. The bison are going to go there too. So I think people were more or less tethered. We don't see a lot of early or middle archaic sites that are scattered out across the plains. They're pretty much confined to springs and clearly near source, streams, rivers, places where there's water. Alluvial fans. Almost every alluvial fan I've dug into has early and middle archaic cultural deposits in it. So, yes.
What is responsible for the current incision, which is exposing these wonderful sections?
I think a lot of it's land use. And the reason I know that or suspect it is that I've looked at the old GLO records, and also where some of the big trails, like the Santa Fe Trail, Oregon Trail, where they crossed. And it was clear that they could cross them easily. But since that time, they're deeply incised, which means most of that incision occurred during historic times. As they started overgrazing, in particular out west, cultivating in the eastern part of the Central Plains, more runoff, which again, it's a real fragile environment. All that loess is so erodible. I think that really ramped up the erosion, headward migration of nick points, and a lot of erosion. I really think that's human driven.
That's an interesting thought, because further west in New Mexico, for example, Leopold and his group, Miller, Wallman, initially thought it was the incision was a result of overgrazing human occupation. But subsequent work, Hereford and others, have suggested that it's a result of a change in storm intensity, and without any change in total rainfall, but just a change in storm intensity.
And the duration of the rainfall, really.
Well, it's the intensity.
Intensity, yeah. Interesting. And there have been multiple periods of incision. It's not just in the historic times, but there was a major episode of incision around between 4,000 and 4,500 years ago, and then another one at 1,000 during the medieval warm period that's been documented in the southern plains and the central plains. But I think the most recent episode of incision, I think, well, it clearly isn't the historic period, and I got to think that humans played a role in that. Of course, we see the legacy sediments in the bottom of the valley. That's the result of all that erosion. Yes.
Do you think that the oxygen isotope composition of your gastropods might reflect precipitation composition? And if so, do you use that to test some of your ideas about atmospheric circulation?
I think yes. The simple answer to that is yes. If I can get somebody to do it. What are you doing? Yeah, I've gotten really good at hustling. No, that's a good idea. I've thought about that. So one of my colleagues, Glenn Fredlin, did that at a site I worked on in South Central Texas. But we also, one student of Art Bettis at University of Iowa actually looked at the freshwater mussels and did auction isotopes 018, 016 did microdrill, like we saw in the previous talk, and got some interesting temperature changes that corresponded pretty much with the isotopes. So, but what you mentioned is a good idea too. You're on. There was another question I thought I saw somewhere else. Right? Yes.
Those patterns of circulation, air mass patterns that we showed from Jim Knox and really derived from the Bryson.
Right.
Or those would have been depicting summer patterns, and,
right.
And they're quite different in other times of the year. But it's easy to, it almost had to be that those summer patterns would have been quite different in the extent that, at least duration, from early Holocene to late Holocene, just because the increased summer insulation because of precession in the early Holocene would have probably led to quite different patterns to the two halves of the Holocene. And so I don't know how that fits into your story, but it seems logical that there would be quite a contrast there. But what it made me think about it is that just north of you in your neighborhood, you've got the sandhills of Nebraska, which have those big dune systems that for a long time were assumed to be late glacial, but turned out to be very young and, a lot of them late Holocene, if I understand it.
Right.
With buried soils. And so how does that fit into the story? So their activity and their activity during a time when things were relatively stable.
Yeah, that's a good question. In fact, I just started working in the sandhills last year. Of course, Swinehart and others have spent a lot of time there. And of course, a lot of that dune activity they've attributed to, especially to the medieval warm period. When you look at their chronology, their OSL dates and their dates on buried soils, I know a lot of that activity they attribute to, and they see alternating periods of drought and where then when it gets more mesic.
There aren't a lot of them in the 3,000 range or something.
There's,
I don't know if they have one.
Yeah, there's some that are 3,000, but it's back and forth. So it would get wet and dry, wet, dry. Which I'm not saying the late Holocene was continuously mesic, but I think compared to the middle and early Holocene, it's cooler and wetter overall, interrupted by periods of aridity. which probably were periods when there was strong zonal flow. We really kind of got locked in with zonal flow. But anyway, actually, like I said, I've just started working with the sandhills and have got some great sections there now that are in some of the alluvial sections there that are buried by dunes. So stay tuned. If I live long enough, we'll see if I can sort that out too, or mess it up. Any other questions? All right, well, thank you very much.